go into what terahertz and what applications is there, so I just want to explain like what the terahertz radiation is. It's just radiation is the frequency of terahertz. Yeah, I remember that. But what are the applications of these terahertz radiations? Recently, within 10 past 10 years, there were work on terahertz sources, detectors, how to utilize the detector, how to improve the efficiency of the detectors. But now it's time to move on, like to concentrate on the applications of terahertz. So in this project, we work on the tunable terahertz devices like terahertz modulator, terahertz polarizer, and finally the terahertz imaging. So what is the use of the terahertz imaging? For example, if you need a structure of any nanoparticle, we just place in the setup, and within some 2 minutes, we'll get the image, structure, chemical composition by using the same setup. So before going to the setup which we used, I would already explain the existing methods. So there are methods for terahertz imaging, like microfabrication process. They used to take the silicon wafer, do the microfabrication of, for example, if you need terahertz imaging of 4x4 pixel, so the microfabrication, the fabrication of split resonators is done for the 4x4 pixels, and then the measurement is performed. And few other methods like, of course, our cameras which we have is like megapixel, but for terahertz range, like we have just started this project, so it's like we are concentrating initially on small resolutions, 4x4 pixels, 6x6 pixels. So the focal plane array was the method which is implemented before. For every pixel, there used to be a detector to detect the terahertz radiation. So since it's a 4x4 pixel, 16 detectors may work. On 6x6, 36. Let us think about high resolutions like 1000 by 1000. So this is quite expensive. And other method is by using mechanical scanning. For example, if we place a nanoparticle in the setup and just start moving the detector slowly to see the structure of the nanoparticle. So this is very time taking, and if we increase the time for terahertz imaging, the problem is there could be a lot of change in the noise, which reduces the efficiency of the setup. So we came up with a new concept with a new setup which reduces the cost, which can be made by using commercial projectors and basically that. So the basic concept of the entire setup is when we have a silicon wafer projects and we project some light, the simple concept of the solar, what happens when light is projected, the atoms in the silicon wafer gets ionized and the electron in the valence shell comes out of the atom. So when light of maximum intensity is projected onto the silicon wafer, lot of electrons will be coming out of the atoms, and this particular part becomes conducting. So this is the key part which we are concentrating on. The terahertz radiation has electric field along y-axis perpendicular to ground. So this electric field is obstructed by the conducting material. So that's the basic concept we use, and the presence and when the intensity of light is increased, the number of electrons in the density of electrons increases. That means the electron plasma is formed. So this is a new experimental setup which we implemented by using a single Schottky detector. Like previously I explained to you, like for 4x4 pixel, 16 pixels. That means 16 detectors. So that's way expensive. But in this setup, we'll be using a single Schottky detector and the commercially available DLP projector. So the terahertz source gives the frequency, the terahertz radiation frequency 570 to 630 gigahertz range, and the parabolic lens are used to focus the terahertz radiation towards the object. The object is placed in this position, like a nanoparticle. We can put a thumb to get the fingerprints, and lot of applications, radio astronomy and medical uses. So this is silicon wafer and a beam splitter. The beam splitter is used to reflect the terahertz radiation, and simultaneously the visible light which comes out of the DLP projector, the digital light processing projector, passes through the beam splitter, and this is a Schottky detector. So this is the entire setup which we implemented for using this one setup, for one detector. So when we see the closely, this is the terahertz radiation, and at point O, the structure which we have to find out is placed, and this is a beam splitter, and we project light of 0% intensity, that is, we project any light. So the silicon wafer is a semi-insulation wafer which allows the terahertz radiation pass through it. Nothing is blocked. So we can see the terahertz radiation is completely transmitted when no light is projected. But as the intensity of light is increased, intensity I meant like the projection in grayscale. 0% intensity means black color light is projected and 100% is just white color. So as the intensity of light is increased, the electron plasma, which the electron density is increased, and thus the terahertz radiation decreases. So we can see that the modulation of 20 dB is obtained at 5 GHz frequency. So this is a proof of concept that the terahertz radiation, the modulation of terahertz radiation is occurring. Then we did the modulation speed, like first the projection of black color light is done, and then the white color. So when the projection is changed, there will be a transition. So we found the time delay as 550 microseconds. Like we can still improve it further, but since it's the first time it is implemented, it's better for now. Then we further move on to the terahertz polarizer. So when the terahertz is when the pattern projected is horizontal to the ground, and when the horizontal lines are projected in a density of 150 lines per inch, it's pretty less. You can still increase it, but as I told you, we start from less number to high number. So the E field of the terahertz radiation is vertical. So when the pattern is projected horizontal to the ground and the E field is perpendicular to it, there will be a lot of transmission. There will be a lot of transmission of terahertz radiation. So that's how we get the maximum E. And as the angle is changed to the vertical position, the terahertz radiation is completely blocked. So the circles represent the experimental results of our project, and it follows simulated results, which is given by Miller's law. It's a cosine vector wave. So these concepts are terahertz modulator. So there is some modulation of terahertz and the polarization in the modulation speed, which this encourages us to move forward for terahertz imaging of a simple 4x4 pixel. So these are two different methods. By first method, the scanning each pixel, what we do is we just place the object behind the silicon wafer in front of the terahertz source, and then each pixel is projected white color. So once I project a white color in the first pixel, at that particular point the terahertz radiation is blocked, and then the second pixel, third. In this way, we project 16 pixels and then find at each and every pixel what exactly is there. If there is an object, there is less transmission. So after we get the recorded transmission at every pixel, then we do the reconstruction of the image, and that's how we got. So this is the metal part which is kept in front of the silicon wafer. It's a bigger in area compared to the nanoparticles which I was saying, but since it's the first time, so we got the image of this metal open part, and the other part is closed, so it's in black color. But there is one problem with the scanning each pixel. Technically, I should call this as a method. So if it is a 4x4, the area of this is 10 by 9 millimeter square. So for 4x4 pixel, it's a pretty 1/16 of the entire area. That's fine, like it can detect. But if you think about 800 by 800, so when we project each pixel, the projected part is so less, it's very less area that we can't see by naked eye as well. So that will be difficult for Schottky detector to find the transmission, because there will be a lot of noise, and there's still work going in to improve the efficiency of the Schottky detector. So we implemented one more method called coded aperture imaging by using the Hadamard imaging. We have Hadamard matrix for every resolution of the pixel, and we project multiple pixels at a time. There is always 50% of the transmission, so that we can see by naked eye that there is some modulation. So by using Hadamard imaging, we got a similar result than that of by scanning each pixel. But as the resolution increases, we can see this imaging is far better than then we were so curious to find the terahertz beam. There are no till now there are no such experimental setups which can show the terahertz beam size at various positions and also the exact diameter in terms of millimeter. So what we did is we placed the silicon wafer at 3 different positions between the parabolic mirror and also the beam splitter. So initially, if it is kept, the silicon wafer is kept in this position, we can see that the size of the diameter of the terahertz radiation is quite bigger. So the reconstructed image shows that. And as the silicon wafer is moved little forward, lesser beam, little forward, lesser diameter. So the simulated results showed that the diameter of at this position is 9 millimeter, 7 millimeter, and 5 millimeter. So we got the similar results by using the experimental methods also. So this helps us to find the size of the mapping of the terahertz beams, which was not existing till now. So finally, by using this setup, we can see that we can use less number of detectors, and by using a commercially available digital light processing projector, the experiment can be performed. And higher applications like communication, sensing, imaging, and this setup is also used to find the vibration of gold particles and many other applications. The further work is to improve the resolution, like the cameras which we have are megapixel. So as the years goes on, we can still keep on improving the terahertz range, and someday there can be terahertz camera as well. I would like to thank Mr. Notre and Dr. Lu advisor for giving us valuable suggestions. Any questions?
Thank you. What program did you use for your simulations? We talk about programming for your simulations.
No, we don't use any programming for simulations. We just use the MATLAB to find the diameter of the Gaussian beam and then relate it with the experimental